everyone, let me know in the chat box. Let me know in the chat box with the thumbs up if I'm audible and visible to everyone. Let me know in the chat box if I'm audible and visible to everyone. Do that fast, do that fast. Do that fast. Okay, that's great, that's great, that's great. Hello Rian, hello Rian. Hi Sakina. Hi Cruz Minati, how are you? Good evening Reena, good evening. Hi Suhail. Vani JD, what's up? Hi Ritu, hi Shagufta, how are you guys doing? Okay, so as you all must be knowing, we are discussing the chapter Electrochemistry, right? And in the last session, we discussed the concepts of the Nernst equation. We did few questions based on the same concepts. And in the today's session, we are only going to solve problems in which the concepts of Nernst equation are used, right? So we are going to solve some good number of problems today, okay, which are based on the concept of the Nernst equation, right? So people, before starting the session, let me introduce myself. My name is Wassim Sir and I'm your chemistry master teacher right here, as you all must be knowing now, right? Yeah. Okay. So do like, share and subscribe at the same time so that everyone gets benefited out of it, which I always say in every class, which is the main motive of creating the channel, as you all must be knowing, right? Yeah. Okay guys, so before starting the session, I need to give you the brief introduction about the Vedantu JEE Pro subscription. What all benefits you guys are going to get if you are going to get enrolled in this Pro subscription. What all benefits will be there for you. Let me tell you, you are going to get 5,000 plus hours of live online teaching. Regular tests and assignments will be provided to you, which contains more than 10,000 questions. We have got 20 plus teachers with 5 plus years of teaching experience who will be constantly helping out, who will be personally training you guys for the JEE 2021 or 2022. Okay, and let me tell you, you have got the complete liberty to learn either in English or in Hindi. Okay, and in this Pro subscription, everything is going to get covered, which includes your micro as well as crash course. Okay. Now, people, for the ones who are going to appear in the JEE in 2021, we have got 3 different plans for you, and you can have a look. For every plan, we have got 20% off. You are getting the 1 month plan just for 6K after the 20% off. 3-month plan you are getting for 16.8K, and 6-month plan you are getting it for 31.2K. Okay, and all these plans are valid for the ones who are going to appear in the JEE in 2021. All right, for the people who are the droppers, let me tell you, we have come up with 3 different plans for you: 1 month, 3 month and 6 month. And in all the 3 plans, we have 20% off, right? And the 1 month plan after the 20% off, it's for 7.2K. 3-month plan after the 20% off, it's for 20.4, and 6-month plan after the 20% off, it is 40.8K, right? All right, and how to avail this 20% off, how to avail this discount, let me tell you, there's a link in your description box. Just click on that link, use the coupon code as WBPRO. By using this coupon code of WBPRO, you guys are going to get the 20% off in every plan, whatever I showed you over here. Okay, so should we start the session, guys? Let me know, should we start the session? Are you super excited for the session? Let me know fast. Thank you, Bharat, thank you. Hi, Banu, good evening. Thank you, Sakina, thank you. Hi, Manmeet. Are you guys super excited for this session? Let me know in the chat box with the thumbs up fast. Let me know in the chat box with the thumbs up fast if you guys are super excited for this session. Yeah? That's great. Good evening, Sayed. Good evening. All right, so let's get started with the first question, which is on your screen now. Okay, the first question which is on our screen. Have a look, guys. See what the question is all about. It's a very simple question. You just need to understand the question, try it out. The question is done. Very, very simple question. Have a look. A zinc electrode is dipped in a 0.1 molar solution of its salt, right? We are having a zinc rod which is dipped in a 0.1 molar solution of its salt at 25 degrees centigrade. Assume the electrolyte is 20% dissociated. Assume the electrolyte is 20% dissociated. Calculate the electrode potential. Calculate the electrode potential, and we are given with the standard reduction potential of zinc. We are given with the standard reduction potential of zinc, right? A very, very simple question. Few things you need to understand right here. First of all, we are supposed to calculate the electrode potential, but it's not mentioned whether we have to calculate the oxidation potential or reduction potential. If it is not mentioned whether we have to calculate the oxidation or reduction potential, that actually means we have to calculate the reduction potential. Whenever it won't be mentioned, whenever it's not going to be mentioned whether we are going to calculate the oxidation or reduction, that actually means we are going to calculate the reduction potential. Okay, first thing. Second thing, I am having a zinc rod right here, right? I'm given with a zinc rod. Let's say this is my zinc rod, and this zinc rod is dipped into a solution. Okay, this zinc rod is dipped into a solution, and solution contains an electrolyte. Solution contains an electrolyte, right? This container contains the electrolyte, and what is the electrolyte all about? We have got the solution of its salt, right? I'm taking salt of the zinc, right? Let's say I'm taking ZnSO4 as the salt over here, correct? So basically, what do I have right here? I have got a zinc rod dipped into its own ions. Why is that? Because we know zinc sulfate, it's considered as a strong electrolyte. It will get dissociated to Zn di positive plus SO4 di negative at the same time, correct? So that means I have got the zinc rod which is dipped into its own ions, and whenever I'll be having a metal rod dipped into its own ions, we call this setup as the electrode. And which electrode is it? It is the zinc electrode right here. Got it? Now people, over here, which potential is given to us? Have a look. Zn di positive, its oxidation state is +2 right here. Oxidation state of zinc right here is 0. +2 to 0 means decrease in oxidation state. Decrease in oxidation state is what we call as a reduction. That means this is the standard reduction potential of zinc. This is the standard reduction potential of zinc. And how do we calculate the reduction potential of any electrode? By means of Nernst equation. The Nernst equation which I'll be using at that time is going to be ERED, which denotes your reduction potential, is always equal to E naught of RED, standard reduction potential, minus 0.0591 divided by N, and this is going to be log of QC. This is the equation by means of which we calculate the reduction potential of any electrode, right? So in order to use this equation, I need the values of E naught RED, which is the standard reduction potential of zinc, which is given to me. I need the value of N. What is N? Number of moles of electrons which are being transferred from anode to cathode. I need the value of QC. All these things I need. All these things I need. Correct? Now, the first thing, the electrolyte which I have right here in the container, let me erase it. The electrolyte which I have right here in the container, which one is it? It is zinc sulfate. And this zinc sulfate got completely dissociated into its ions, Zn di positive aqueous plus SO4 di negative aqueous, right? Now people, this is the reaction which is going to happen. Now first of all, in the question, it's mentioned that only 20% of the electrolyte is getting dissociated. Only 20% of the electrolyte is getting dissociated. If 20% of the electrolyte is getting dissociated, can I say degree of dissociation is going to be simply 0.2? Degree of dissociation, which I represent by alpha. What is degree of dissociation all about? Degree of dissociation of any electrolyte is always equal to percentage dissociation. Percentage dissociation divided by 100, as you all must be knowing, something which you would have discussed in ionic equilibrium, right? Now people, at time t is equal to 0, if I'll ask you what was the concentration of ZnSO4, the concentration of ZnSO4 was 0.1 molar at time t is equal to 0. What about the concentration of Zn di positive at time t is equal to 0? This is 0, this is 0. Very, very simple. Correct? Now people, this is the value of C. This is the value of C. As you would have discussed in your ionic equilibrium, right? This is going to be C minus C alpha, this is going to be C alpha, this is going to be C alpha. Very, very simple. Something which you would have discussed, right? If this is C, 0, 0, this is going to be C minus C alpha, this is going to be C alpha, this is going to be C alpha, right? I know the values, I know the value of C, I know the value of alpha. Can I simply calculate the value of C alpha? And what is this C alpha? C alpha will give me the concentration of Zn di positive into the solution when 20% of electrolyte is dissociated. When 20% of the electrolyte is dissociated, right? So what am I going to do? Have a look guys. I'm going to write concentration of Zn di positive. I got to know that is equal to C alpha. C value already you guys know, that is equal to 0.1. Alpha value you guys know, that is equal to 0.2. So concentration of Zn di positive in the container is going to be 0.02 molar. 0.02 molar. Correct? When the electrolyte is 20% dissociated. Now I'm going to do the equation. Right? See guys, what are we supposed to calculate? We are supposed to calculate reduction potential. That means in order to calculate the reduction potential, this zinc electrode which is given to us, it has to act like the cathode. It has to act like the cathode. If the zinc electrode has to act like the cathode, then which reaction has to take place there? A reduction reaction should take place, right? If the zinc electrode is acting like the cathode. What is the reduction reaction of zinc electrode all about? The reduction reaction of zinc electrode is Zn di positive aqueous plus 2 electrons change to zinc. This is the reaction which is going to take place in the zinc electrode when zinc electrode is going to act like the cathode. Very, very simple, right? Now people, how many electrons are being exchanged in this reaction? 2 electrons are getting exchanged. So this 2 is going to be the value of N first of all. This 2 is going to be the value of N. Now for this reaction, can we write the expression for QC? Definitely. QC is going to be product over here is in solid form. Its active mass is 1. Divided by this Zn di positive in aqueous form. So I'm going to use concentration of Zn di positive raised by its stoichiometric coefficient, which is 1. Concentration of Zn di positive, we got to know how much is that? That is 0.02. That is 0.02. Or I'm going to write it like this. I'm going to write it as 100 divided by 2, which is equal to 50. Which is equal to 50. This 50 is the value of QC right here. This 50 is the value of what? This is the value of QC right here. Got it? I got the value of QC, I got the value of N, standard reduction potential of zinc electrode is given to me. Can I simply use all the values into the equation? If I'll use all the values into the equation, I'll be getting the reduction potential of zinc electrode, which will be E0 reduction, SRP, standard reduction potential of zinc, which is minus 0.76 volts, minus 0.76 volts, right? Minus 0.0591 divided by value of N. Value of N, all of you must be knowing, that is 2. This is going to be log of QC. What is QC value? QC value is 50, correct? This 50 you can write as 5 multiplied by 10. 5 multiplied by 10. Then you will be using log of M multiplied by N formula, correct? You have all the values. On solving all the values, can I get the value of E reduction, which denotes your reduction potential of zinc electrode, which we were supposed to calculate, and the units is going to be in volts. Got it? Let me know in the chat box if it is clear. Let me know in the chat box if it is clear to you. Let me know in the chat box if it is clear to you. Let me know with the thumbs up fast. Let me know with the thumbs up if it is clear to you. Fast, fast, fast. Let me know fast, guys, if it is clear to you. Yeah? That's great. That's great. So what am I going to do is, I'm going to move to the next question. I'm going to move to the next question, right? Matthew, it is simple. It is log of 50. Log of 50, you can write it like this. Log of 50, you can write it as log of 5 multiplied by 10. Log of 5 multiplied by 10. M multiplied by N, which is going to be equal to log of M plus log of N. This value is equal to 1. Log of 5 value you already know. You just put all the values into this equation. You will get the reduction potential. Very, very simple. Correct? Okay. Banu Prakash got the value as 0.81. Chalo, Banu Prakash, I trust you. Okay. Chalo, Banu Prakash is saying it's coming as 0.81 volts. Okay. Let's assume the answer is coming as 0.81 volts. Right? Okay. I'm moving on to one more question, guys. This was a simpler one. Correct? I'm moving on to one more question. Have a look. This question you can only solve if you would have studied the ionic equilibrium in class 11th, right? See guys, we are given with a reaction. CH3CHO. Was this the question? I think before this one more question was there, right? Just a second. Yeah, this question. Okay, see guys, what are we given with? First of all, we are given with this value, E naught of Cu di positive change to Cu. Is it the standard reduction potential of copper or standard oxidation potential of copper? See guys, very simple. The oxidation state of copper right here is +2. The oxidation state of copper right here is 0. So from +2 to 0, oxidation state is decreasing. Decrease in the oxidation state is what we call as reduction potential. Decrease in the oxidation state is what we call as reduction. So this value is your standard reduction potential of copper. This is standard reduction potential of copper which is given to us, right? Calculate the reduction potential at pH equal to 14. Calculate the reduction potential of the copper electrode when the pH of the solution is 14, correct, at 25 degrees centigrade, correct. KSP value for CuOH is given as 10 power minus 19. First of all, what are we supposed to calculate? We are supposed to calculate reduction potential of the copper electrode, correct? We are supposed to calculate reduction potential of the copper electrode. So what is the equation? What is the Nernst equation which I'm going to use? I'll be using this equation. Reduction potential of copper electrode is going to be equal to standard reduction potential of copper electrode minus 0.0591 divided by N log of QC, right? This is the equation which I'll be using in order to calculate the reduction potential of the copper electrode. Very, very simple. First thing, E naught of reduction. Standard reduction potential of copper is given to me. That is 0.34. I am supposed to calculate the value of N. I am supposed to calculate the value of QC, right? These things I have to calculate first. Now, first of all, since I have to calculate the reduction potential of copper electrode, so copper electrode is going to behave like the cathode right now. If the copper electrode is going to behave like the cathode, reduction has to happen, correct? And what is the reduction reaction of copper? All of you must be knowing. It is Cu di positive aqueous. Cu di positive aqueous plus 2 electrons change to copper solid. This is the reaction which should take place when this copper electrode will be acting like the cathode, correct? Very, very simple. Now people, how many electrons are being exchanged over here? 2 electrons are being exchanged. So this 2 is going to be the value of N right here. This 2 is going to be the value of N right here. Okay, N value I got, which is equal to 2. This is the value of N. Now, after this, I'm going to write the reaction quotient expression. I'll be starting from the product, correct? See, over here, product is in solid form. So its active mass is going to be unity. 1 divided by Cu di positive aqueous. So it's going to be concentration of Cu di positive. It's going to be concentration of Cu di positive to the power 1. Now, is the concentration of Cu di positive given in the equation? No way, it's not given, correct? Concentration of Cu di positive is not given. So what am I supposed to do? I'm supposed to calculate it by somehow. And how do I calculate it? There are some few more values given to me. I have to use these values and somehow I have to get Cu di positive concentration. And what am I going to do now? Have a look, guys. The first thing, the pH of the solution is given to me. pH of the solution is given to be 14. Correct? If pH is equal to 14, you would have studied this relation. H positive concentration is equal to 10 to the power minus pH. Have you studied this? If pH of the solution is given, you can calculate directly the H positive concentration. So H positive concentration in the solution is going to be 10 to the power minus 14. Now the reaction, the cell is at 25 degrees centigrade. There is one more relation which you would have discussed in the ionic equilibrium. At 25 degrees centigrade, H positive concentration multiplied by OH negative concentration is always equal to 10 to the power minus 14. Have you studied this one as well? Have you discussed this? Right? This is valid at 25 degrees centigrade, right? Very, very, very simple. Okay. Now people, H positive concentration we have, that is 10 power minus 14. So can I get from here OH negative concentration? OH negative concentration I'll get as 10 power minus 14 divided by H positive concentration, which is again 10 power minus 14. Value is going to come as 1. So 1 is the OH negative concentration which I got right here. 1 is the OH negative concentration which I got right here. Very simple. Correct? 1 is the OH negative concentration which I got right here. Correct? Now people, after this, what am I going to do with this? What am I going to do with this OH negative concentration? I need Cu dye positive concentration, okay? So what am I going to do with this OH negative? See, what am I going to do? I'm going to erase this part. I'm going to erase this part. I'm sure this is clear to you. OH negative concentration I got as 1, correct? OH negative concentration I got equal to 1. Now people, Ksp of CuOH whole twice is given as 10 power minus 19. First of all, what is this Ksp? Ksp is what we call a solubility product, right? Ksp, as you guys might be remembering, in your ionic equilibrium, there is one term called as Ksp, solubility product, right? This CuOH, right now, it's a sparingly soluble salt, correct? It's a sparingly soluble salt, CuOH whole twice, okay? And what will be the ions? Its ions are going to be Cu dye positive aqueous plus Cu dye positive aqueous plus twice OH negative aqueous plus twice OH negative aqueous. This is something, correct? Now people, at the same time, have a look. Understand one thing. See, first of all, CuOH whole twice, it's getting dissociated to what? Cu dye positive plus twice OH negative. If I want to write the expression for Ksp, if you guys remember, how do we write the expression for Ksp? Expression for Ksp will be written as concentration of Cu dye positive raised par stoichiometric coefficient multiplied by concentration of OH negative raised par the stoichiometric coefficient, that is 2. Correct? Is the Ksp value for CuOH given to me? Definitely 10 power minus 19 will be equal. Concentration of Cu dye positive right here, correct? OH negative concentration, we got it as 1, right? OH negative concentration, we got it as 1. So this whole term is 1. So can I get the Cu dye positive concentration right here? Cu dye positive concentration I got as 10 power minus 19, correct? I got the Cu dye positive concentration. So Qc value is going to be simply 10 power 19, right? Qc value is simply going to be equal to 10 power 19. Now, do we have all the values? In order to calculate the reduction potential, we should have standard reduction potential of copper electrode, which is given to me, right? Minus 0.0591 divided by N. N value I got as 2. Log of Qc. Qc value I got as 10 power 19. Can you solve this further? Can you solve this further and get the reduction potential of the copper electrode? I hope you got it. I hope you got it. I hope you got it. Yeah? Let me know in the chat box if it's clear to you guys. Let me know in the chat box. Let me know in the chat box fast if it's clear to you. Wonderful, guys. Okay. I'm moving on to one more question. See, all the values you have here, right? We have to calculate this reduction potential of copper electrode. E naught RED is given to me. N value I got. QC value I got. Everything I got. I just have to put the values into the equation. I'll get the reduction potential over here. Correct? Now, guys, I'm moving on to one more question. Let me see if we can solve this or not. I'm given with a reaction CH3CHO. Let me write the reaction first. I'm given with CH3, or let's not write it so that I can use the space. CH3CHO, whose concentration is 1 molar, which is given to me, plus twice H positive aqueous plus 2 electrons, changed to CH3CH2OH, whose concentration is 1 molar. Correct? The half cell potential is this much. What do we mean by this? First thing, if I ask you, is this a reduction reaction or oxidation reaction? Electrons are being gained. So this is the reduction reaction. So this cell potential means he's talking about what? He's talking about the reduction potential. So reduction potential of the electrode whose reaction is this is minus 0.197 at pH is equal to 7. Calculate the half cell potential at pH is equal to 6 when the concentration of this is equal to 10 power minus 5 molar. Can we do it? What do you guys think? Can we do this question? What do you guys think? It's a very simple question, guys. First of all, how many electrons are being exchanged in this reaction? 2 electrons are being exchanged. So I would say the value of N, first of all, I got as 2. Okay. Now people, if I'll ask you, what is going to be the expression for QC for the reaction? What is going to be the expression for QC? Over here, concentration is 1 molar, right? It's going to be 1 divided by. Over here, concentration is 1 molar, and this is H positive, so this is going to be H positive concentration raised power 2. H positive concentration raised power 2. QC expression I got for the reaction. N value over here I got as 2. N value over here I got as 2. And I'm given with the cell potential. That means I'm given with the reduction potential because this is a reduction reaction. Okay. And at the same time, what am I given? See, the reduction potential of this electrode, I'm writing it like this, ERED, the reduction potential of the electrode for which the cell reaction is this. It is given as minus 0.197 volts when the pH of the solution, is 7. When the pH of the solution is 7. Correct? Now guys, understand what I'm going to do. Or let me erase this part first. Let's try to simplify the equation. See, first of all, if I'll write the Nernst equation for the electrode, what will be my Nernst equation for the electrode? See guys, see what is going to be my Nernst equation for the electrode. Have a look. And since it's a reduction reaction, so I'm going to write ERED, reduction potential of the electrode, is equal to E naught of RED minus 0.0591 divided by N log of QC. What is the expression for QC for this reaction? It is 1 upon H positive concentration. Can I write it like this? H positive concentration to the power minus 2. I can write it very, very simple. Correct? I can write it. Now people, I can write it like this also. ERED, reduction potential of the electrode whose cell reaction is given to us, is going to be equal to standard reduction potential of the same electrode minus 0.0591 divided by. What is the value of N for it? Value of N for it is 2. This is log of M to the power N, which is going to be equal to N log of M. N log of M. Correct? This is something which I'll be getting over here. Can I say this 2 and this 2 will get cancelled out? And when this and this 2 and this 2 will get cancelled out, I will get it like this. Reduction potential of the electrode is going to be equal to standard reduction potential of the electrode minus 0.0591. Minus 0.0591. This is minus log of H positive. Minus log of H positive is what we call as pH, if you remember. Minus log of H positive is what we call as pH, if you remember. So I got a general equation over here. For this cell reaction. This is my general equation. Now I am going to put the conditions in this general equation. Whatever conditions are given to me, I'm going to put those general conditions for this equation which I got. See guys, how am I going to solve this question now? I'm sure till now it's clear to everyone. Just a second. Just a second, guys. Just a second. This is the net equation which I got. Now, people, in the question, it's mentioned that the half cell potential, that means the reduction potential of the cell is minus 0.197 volt at pH is equal to 7. So this condition I'm going to use. This is my first condition. This condition I'm going to use in my equation. Reduction potential of the electrode is minus 0.197 volts. When is the reduction potential of the electrode minus 0.197 volts? When the pH of the solution, 0.0591, when the pH of the solution was equal to 7, let me call this as equation number 1. What we have to calculate? Calculate the half cell potential at pH 6. That means we have to calculate the reduction potential of the same electrode at pH equal to 6. Very, very simple. Okay, at pH equal to 6. So what am I going to do? I'm going to put this condition in the general form which I got over here. I'm going to put the condition in the general equation which I got over here. I'm going to write the reduction potential of the same electrode, and when do we have to calculate it? When the pH of the solution is going to be how much? When the pH of the solution is going to be 6. Correct? I got equation number 2, right? Now people, if I'll simply subtract these two equations, what all things will get cancelled out? Very, very simple. Subtracting first from second. If I'm subtracting first from second, this is going to be positive. This is going to be negative, this is going to be positive. Can I say this value and this value will get cancelled out? So what I'll be left with? I'll be left with reduction potential of the electrode at pH is equal to 6. Correct? This is the reduction potential of the electrode when the pH of the solution is 6. And it's going to be plus 0.197 volts is equal. It's going to be 0.0591. I'm taking common, and over here it is going to be 7 minus 6. Okay, so can't we get the value of reduction potential? Can't we get the value of reduction potential from this equation? Very simple. Got it? Is it clear? Is it clear to everyone, guys? Let me know in the chat box fast. Is it clear? See, guys, this value is equal to 1. This value is equal to 1, correct? So I can say the reduction potential of the electrode whose reaction was given to us when the pH of the solution is 6 is going to be equal to 0.0591 minus 0.197. The value is going to come as negative, and let me know the answer in volts. Let me know the answer in volts fast. Let me know the answer in volts fast. Banu Prakash is saying it is 0.8 volts. Is that? Maybe it can be 0.8 volts only then. So, okay, minus 0.8 volts will be the reduction potential of the electrode whose cell reaction was given to us at when the pH of the solution was 6. The different world. Wassim Sir, chemical bonding, please. Surely I'll be starting chemical bonding from the next week. Okay? So, relax. Alright, guys. I'm moving on to one more question then. Let me see if you can solve this question or not. It's a very simple question, and I want every one of you to give it a try. Again, I'm given with a reaction. I'm given with a reaction, correct? And is this the reduction reaction or oxidation reaction? It is the reduction reaction because electron is being gained over here, correct? And I'm given with the standard SRP. I'm given with the standard reduction potential over here of this cell, correct? Calculate the reduction potential in the neutral solution when the pH is equal to 7. Again, a very simple question. Understand what I'm going to do. Have a look, guys. This is the reaction which is given to me. First of all, over here, one electron is exchanged. So N value over here is 1. First thing. Okay. What am I supposed to calculate? Reduction potential. So I'm going to use the equation. Reduction potential of the electrode whose reaction is this one is going to be equal to standard reduction potential of the same electrode minus 0.0591 divided by N value over here is 1 log of QC. What is the value of QC? I'll start from the product. This water I'm not considering because it is in liquid state. Okay, NO2 gas, its partial pressure is how much? Its partial pressure is 1 bar divided by NO3 negative aqueous, its concentration is again 1 molar raised by stoichiometric coefficient, that is 1, correct? Multiplied by concentration of H positive to the power stoichiometric coefficient, that is 2, correct? Now, guys, have a look. I'm writing like this: reduction potential of the electrode whose cell reaction is this, right, is going to be equal to E naught of RED minus 0.0591. This is log of 1 by H positive square. Can I write it as log of concentration of H positive to the power minus 2? I can write it like this. Can't I? I can do that. Correct? I can write it like this: log of H positive concentration to the power minus 2. Very simple. Now, guys, have a look. I can write the equation like this: reduction potential of the electrode is going to be equal to standard reduction potential minus 0.0591 log of M to the power N, which is going to be N log M, right? Very simple. Now, people, I can further write it like this: reduction potential of the electrode whose cell reaction is given to me is going to be equal to E naught of reduction minus, I'm keeping there only 2, I'll come to the front. 2 will come to the front and 0.0591 over here. This becomes minus log of H positive. Minus log of H positive is what we call as pH. Correct? This is what we call as pH. Okay, and pH of the solution is given to me, right? The solution is neutral, right? pH is equal to 7. So I have to put the pH value equal to 7. I'll get the reduction potential. Very, very simple. So I'm going to get reduction potential over here as standard SRP, standard reduction potential. Standard reduction potential of the electrode whose cell reaction is this one. It is 0.78, right? Minus 2 multiplied by 0.0591 multiplied by pH of the solution, which is right now how much? Which is right now 7. Can we solve this one and get the answer? You just have to solve this one. You will get the reduction potential of the electrode when the solution will be neutral. When the solution will be neutral. Let me know fast. Let me know fast what is the answer coming. Let me know fast what the answer is coming. VSG is saying it is minus 0.07 something. Banu is saying 11.6. Thank you, Muzaffar. Thank you. Okay, Banu is saying minus 11.6. Is that? Okay, you just calculate it, guys. You just calculate it. I mean, you can do it afterwards, right? You can do it afterwards, right? You can do it afterwards. Okay. I'm moving on to the next question, guys. Just solve this. That will be giving you the reduction potential of the electrode whose cell reaction is this one. And when you are calculating that reduction potential, when the solution pH is 7. When the pH of the solution is 7. Okay? You just calculate it afterwards. Banu Prakash is saying minus 11.7. VSG is saying minus 0.047. What is it? What is it? What is it, guys? Okay, you just do the calculation but afterwards and let me know the answer, okay? Alright, I'm moving on to one more question, guys. I'm moving on to one more question. Let's see what the question is. Okay. Have a look on one more question, guys. See, how much does the reduction potential of 1 molar MnO4 negative, which is changing to Mn di positive, Mn di positive concentration is again 1 molar couple, change if H positive concentration is decreased from 1 molar to 10 to the power minus 5 molar at 25 degrees centigrade. Can we do it? Can we do it? Let me know in the chat box. Can we do it? Can we do it, guys? What do you think? What do you think? Can we do it? We have to check how much reduction potential of this electrode is going to get decreased if I'll change the H positive concentration of the solution from 1 molar to 10 to the power minus 4 molar. Correct? See, guys, have a look. First thing, the electrode which is given to me, right? The electrode which is given to me. Over here, the oxidation state of Mn is plus 7. Over here, the oxidation state of Mn is plus 2. Right? Plus 7 to plus 2, decrease in oxidation state. Plus 7 to plus 2, decrease in oxidation state. Decrease in oxidation state means reduction, right? So first of all, I'm going to write the reaction. I'm going to write the reaction first. MnO4 negative is getting converted to what? It is getting converted to Mn di positive. Mn di positive aqueous. Correct? MnO4 negative aqueous is getting converted to Mn di positive aqueous. Now, first of all, which reaction is it? Plus 7 to plus 2. Plus 7 to plus 2, right? Plus 7 to plus 2. It's a reduction reaction. It's a reduction reaction. In the reduction reaction, there must be gain of electrons. In the reduction reaction, there must be gain of electrons, right? Now the first thing, how many electrons are being gained? How many electrons are being gained over here in this reaction? Have a look, guys. First of all, the oxidation state over here is plus 7 and over here it is plus 2. This plus 2 is the final oxygen state. This plus 7 is the initial oxygen state. If I'll ask you what is the change in the oxidation state, that's going to be final oxygen state minus initial oxygen state. The change is coming as 5. So 5 electrons are being gained over here by this MnO4 negative. 5 electrons are being gained. Now if I'll ask you, is this reaction balanced or not? Is this reaction balanced or not? Okay. The reaction is not balanced and the reaction is taking place in acidic medium, right? The reaction is taking place in acidic medium. So I'm supposed to balance this reaction in acidic medium. Over here we have got 4 oxygen. So I'm adding over here as 4 times H2O liquid. Now people, I got 8 hydrogens. So I'm going to write over here as 8 H positive ions, 8 H positive aqueous ions. The reaction is balanced. Correct? The reaction is balanced. Now the reaction is balanced. Just a second. Now the reaction is balanced. Okay, understand what I'm going to say now. Understand that properly. First of all, what is the value of n over here? How many electrons are being exchanged? 5 electrons are being exchanged over here, correct? 5 electrons are being exchanged right here. Okay, if I'll ask you to write the reaction quotient expression, how would you write the reaction quotient expression? Very, very simple. The reaction quotient expression is going to be QC is equal. I'll be starting from the product. This is going to be concentration of Mn di positive. Concentration of Mn di positive. This is water in liquid state, nothing to do with it. Divided by, this is concentration of H positive to the power 8. Right? And this is concentration of MnO4 negative to the power 1. Correct? Very, very simple. Now people, is the concentration of Mn di positive given to you? The concentration of Mn di positive is given to you. That is 1 molar. Divided by H positive concentration I'm keeping as such. Or should we use the H positive concentration over here only? No, let's keep the H positive concentration as such. Okay? H positive concentration I'm keeping as such. MnO4 negative concentration is 1 molar multiplied by 1. Correct? So QC value over here I got as concentration of H positive to the power minus 8. Okay? Now people, we have to check how much reduction potential is decreasing when the H positive concentration is changing from 1 molar to 10 to the power minus 4 molar. First of all, I'm going to write the Nernst equation, right? I'm going to write reduction potential of the electrode is going to be equal to standard reduction potential E naught RED minus 0.0591 divided by N value. What is the N value? N value over here is 5. This is going to be log of concentration of H positive to the power minus 8. This is something which I got right here. This is something which I got right here. Very simple. Now let me simplify this a bit. Let me simplify it a bit. It is going to be reduction potential of the electrode which is given to me is equal to standard reduction potential of the electrode minus 0.0591 divided by 5. Log of m to the power n. That's going to be equal to n log m. That's going to be equal to n log of m. Okay, like this. Correct? Very, very, very simple. Now people, let me erase this part. Let me erase this part over here. Let me erase this part. Let me show you how this question is done. See, I got reduction potential of the electrode which is given to me is equal to E naught reduction, standard reduction potential of the electrode, right? Minus 0.0591. Minus 0.0591. Or let me keep this as minus becomes plus. So this is plus. This is multiplied by 8, this is divided by 5, correct? And it's going to be log of H positive concentration. This is the equation which I got till now. This is the equation which I got finally till now. Now I am going to use the conditions in it. See how am I going to use the conditions. First thing, when H positive concentration was decreased from 1 molar to 10 to the power minus 4 molar. First, let me see when the concentration of H positive was 1 molar, what was the reduction potential of electrode? I'm writing if the concentration of H positive is equal to 1 molar, let me see how much was the reduction potential at that time. I'm going to write ERED will be equal to E naught of RED. I'm going to write ERED is going to be equal to E naught of RED. Why? Because concentration of H positive I'm keeping as 1, log of 1 is 0, this whole term will become 0. So reduction potential of the electrode which is given to me is equal to standard reduction potential of it when the concentration of H positive is kept as 1 molar, correct? When the concentration of H positive is kept as 1 molar. Now people, when I'm changing the concentration from 1 molar to 10 to the power minus 4 molar. Now if the concentration of H positive is kept as 10 to the power how much? 10 to the power minus 4. Just use the condition in the equation. Just check how much reduction potential value will come. Reduction potential value will come as E naught RED minus, it's not minus, it's plus 0.0591 divided by 5 multiplied by 8. This is log of H positive. Now it will become log of H positive concentration, which is right now 10 to the power minus 4. So finally, what am I going to get? Understand it properly. I'm going to get it like this. Reduction potential of the electrode will be equal to standard reduction potential. Okay, this is log of m to the power n. Log of m to the power n, correct? So it's going to be n log m. This minus will come to the front. So it's going to be 0.0591 divided by 5 multiplied by 8 multiplied by 4. Log of 10 is going to be 1. Log of 10 is going to be 1. So what are you guys? What are you guys looking? What are you guys looking? See, very simple thing. When the concentration of H positive was 1 molar, the reduction potential of the electrode was equal to standard reduction potential. Now, when I change the concentration of H positive from 1 to 10 to the power minus 4, is the reduction potential of electrode same or reduction potential has decreased? Initially, it was equal to E naught RED. Now it is equal to E naught RED minus this part, correct? Minus this part. So I would say when the concentration of H positive was changed from 1 molar to 10 to the power minus 4 molar, the reduction potential has actually decreased. And how much? By how much volt it has decreased? By this much amount, by this much volt it has decreased, correct? Just calculate it and let me know the value of this part. Let me know the value of this part fast. Let me know the value of this part fast. Yes, Techo Gaming, yes, absolutely. Thank you, Electro King. VSG is saying this value is coming as 0.37. Is that? Okay. So people, this value is coming as 0.37. It is coming as 0.37. That means when the H positive concentration was changed from 1 molar to 10 to the power minus 4 molar, the reduction potential of the electrode is decreased by 0.37 volts, right? Reduction potential is decreased by 0.37 volts, correct? Is it clear to everyone? Let me know in the chat box fast. Let me know in the chat box if it is clear to you. Let me know in the chat box if it is clear to you. Let me know in the chat box if it is clear to you. Wonderful, guys. Great. Okay, so let's move on to one more then. Let's move on to one more question. Let me see if you can solve this or not. Let me see if you can solve this or not. We are given with two reactions, right? NO3 negative, it changed to NO2 in acidic medium. Then second reaction, NO3 negative changed to NH2OH in acidic medium, right? We are given with the standard reduction potential values over here. At what pH the two cells will have same reduction potential? Assume the concentration of all the other species to be unity. Assume the concentration of all the ions to be unity. This is your homework. This question is your homework. And I want everyone to give it a try because it's a simple question. I'm given with two reactions. Both the reactions are happening in acidic medium. I have to check at what pH the two cells will have same reduction potential, correct? I just have to make two equations right here by using Nernst equations. I have to equate those two. I'll get the value, correct? Very, very simple. Exactly, VSG. We have to equate the potentials. Exactly. This is your homework, guys. And you guys are going to give me the answer of this question in the comment box afterwards. I'm moving on to next question. Because it's a simple question and all of you, I mean, you guys can try this out. The guys can solve it out. Let me know the answer in the comment box afterwards. That's welcome, Yashwini. Welcome. Bhanu Prakash is saying 0.07. Bro, I have no idea what the answer is. Let me know. Let me know in the chat box. I mean, comment box afterwards. All right, guys. I've got one more question. See, till now, we were writing the Nernst equation for half cells. Till now, we were writing the Nernst equation for electrodes, right? For one electrode is called as one half cell, right? One electrode is called as one half cell. Till now, we were writing the Nernst equation for the electrodes, for the half cells. Now, I'll show you how to write the Nernst equation for a complete cell, for a complete galvanic cell, okay? In a galvanic cell, in a complete cell, we have got two electrodes which are connected externally and internally by means of salt bridge, right? Now let me show you how to write the Nernst equation for a complete cell over here. Okay? See guys, first of all, this is the salt bridge. On the salt bridge, I always write the anode. This is my anode. And what is my cathode? That means this should be my cathode. At anode, oxidation takes place. At cathode, reduction takes place. I'm given with some values as well. Sn di positive change to Sn. That means SRP of it is given. This is the SRP value of tin. Pb di positive change to Pb. This is the SRP value of lead, right? Because plus 2 to 0. Plus 2 to 0. Decrease in oxygen state. Reduction. That means this is the reduction potential. Standard reduction potential. These two values are given to me, correct? Now have a look. See. First of all, I'm going to show you how to write the Nernst equation. How to write the Nernst equation and how to calculate the EMF of a complete cell. It's a very simple question, guys. Understand properly. First thing, on the left-hand side of the salt bridge, I have got anode, right? And at anode, you all must be knowing, at anode, what takes place? Oxidation takes place. And oxidation of tin is taking place from 0 to plus 2. From 0 to plus 2. So what should be the reaction? The reaction should be tin solid should get converted to Sn di positive aqueous. Sn di positive aqueous plus how many electrons? Plus 2 electrons. This is the reaction which has to take place at anode. Correct? Now about the cathode. What reaction should take place at the cathode? At cathode, reduction will take place. Pb di positive change to Pb solid. So I'm going to write it like this. Pb di positive aqueous plus 2 electrons. It is changing to what? It is changing to Pb solid because reduction is taking place. Reduction means gain of electrons, right? Now people, can I directly add these two reactions? Definitely. Why is that? Because electrons are balanced on both the sides. I can directly add them. So what is the net cell reaction which I'll be getting? Net cell reaction is going to be tin solid plus Pb di positive aqueous plus Pb di positive aqueous. It gets converted to what? Sn di positive aqueous plus what? Plus Pb solid. This is something which I got as the net cell reaction. Okay, and how many electrons are getting cancelled out over here? 2 electrons are getting cancelled. So I would say N value, the number of moles of electrons which are being transferred from anode to cathode, okay, that is equal to 2 because 2 electrons are getting cancelled out. As I told you in the last sessions also, the number of electrons which get cancelled out, that gives you the value of N, correct? Now people, can I write the QC expression for the net cell reaction? I can do that. I'll start from the product. It is going to be equal to concentration of Sn di positive. This is Pb solid, active mass 1 divided by concentration of Pb di positive. Am I given with the concentrations of both the ions? Sn di positive concentration is given as 1. Pb di positive concentration is given as 10 power minus 3. Correct? So the value is going to come as 10 power 3. This is the QC value which I got. Correct? QC value which I got. Now people, in order to use the Nernst equation, I should have one more value, that is E naught cell, standard EMF of the cell, which is always equal to E naught of cathode minus E naught of anode. And in the last session, I told you we have to use SRP values, standard reduction potential values for both the electrodes. We have to use the standard reduction potential values for both the electrodes. Cathode, what is the standard reduction potential value of cathode? Cathode is this lead electrode. What is the standard reduction potential of lead electrode? Is it minus 0.13? Definitely it is minus 0.13. Minus times E naught of anode, standard reduction potential of anode, which is minus 0.14. It is minus 0.14, right? So the value will be how much? 0.01 volts is going to be E naught cell. I got the E naught cell. I got the standard EMF of the cell. I got the standard EMF of the cell. Now, I'll simply use the Nernst equation to calculate the E cell, which is what we are supposed to calculate. I'm going to erase all this. I'm sure this is clear. Now I'm going to use my Nernst equation to get the final answer. As per my Nernst equation, E cell, EMF of the complete cell is always equal to E naught cell minus 0.0591 divided by value N multiplied by log of QC. This is the equation which we write whenever we are supposed to calculate the EMF of the cell. Very simple. This E cell value we have to calculate. Have we calculated E naught cell value? Definitely. E naught cell value we have calculated at 0.01 minus 0.0591 divided by N value. What is this N? N was the number of electrons exchanged. Number of electrons, number of moles of electrons transferred from anode to cathode, which was equal to 2. Correct? Which was equal to 2. This is going to be log of QC. QC value already I got to know. How much is that? QC value I got to know as 10 power 3. Correct? Can't you solve this one and get the answer now? We can solve this one and get the answer. We can solve this question and get the answer. So I can write E cell is going to be equal 0.01 minus 0.0591 divided by 2. This is log of m to the power n, which is going to be n log m. Log 10 is 1. So you just have to solve this value. You'll get the answer. You'll get the EMF of the cell in volts. You'll get the EMF of the cell in volts. Let me know in the chat box if it is clear to you or not. Let me know in the chat box if it is clear to you or not, so that I can move ahead on the next question. Let me know in the chat box. Okay. It's clear, right? That's great, that's great. That's great. All right, whatever answer is getting, just keep the answer, okay? I mean, this much calculation you have to do, guys. That's it. 3 multiplied by this, divided by 2, then minus this, done. That's it. I'm moving on to one more question then. Let me see if you have a few more questions or not. Okay, yeah, one more question we have. In the same way we can do this. We have to calculate the EMF of the cell. We have to calculate the EMF of the cell, right? We are given with one complete cell. We are given with one complete cell. This is the salt bridge, right? And on the left hand side of the salt bridge, we always write the anode. On the right hand side of the salt bridge, we always write the cathode. So we have the anode, we have the cathode. So first thing, what am I going to write? I'm going to write the reaction which will be taking place at anode. At anode, we know oxidation will take place. Oxidation of what is taking place? 0 to plus 1. 0 to plus 1. Increase in oxygen state, right? So what should be the reaction? H2 gas should get converted to what? It should get converted to twice H positive aqueous plus how many electrons it should give? It should give 2 electrons. This is the reaction which should take place at anode. Similarly, if I'll ask you, what is the reaction which is going to take place at cathode? What is the reaction which should take place at the cathode? What is the reaction which should take place at the cathode? Fe tripositive is changing to Fe dipositive. Fe tripositive aqueous is changing to what? It is getting converted to Fe dipositive aqueous. This is the reaction which is taking place at cathode. At cathode, reduction takes place, so it has to gain 1 electron. Now people, can I simply add these two reactions? Can I simply add these two reactions? What do you think? Can I simply add these two reactions? I cannot add these two reactions because the electrons are not balanced. So in order to balance the electrons, I'm going to multiply the second reaction by 2. Then only reactions will get balanced. Okay. After multiplying it by 2, let me add the reactions. So I'm going to get H2 gas plus twice Fe tripositive aqueous plus twice Fe tripositive aqueous. It gives what? It gives twice H positive aqueous plus twice H positive aqueous plus twice Fe dipositive aqueous. This is my net cell reaction. And for this net cell reaction, what is the value of N? How many electrons got cancelled out? Basically 2 electrons, right? I multiplied this reaction by 2. So 2 multiplied by 1 is 2. 2 electrons got cancelled. So N value for the net cell reaction I got as 2. N value for the net cell reaction I got as 2. If I want you to calculate the reaction quotient over here, I'll start from the product. Concentration of H positive to the power stoichiometric coefficient, that is 2, multiplied by concentration of Fe dipositive to the power stoichiometric coefficient, that is 2, divided by, this is gas, H2 gas, its pressure is given to me, H2 gas, its pressure, right? I'm going to use pressure of H2 gas, correct? Because it's in gaseous state, multiplied by Fe tripositive, concentration of Fe tripositive raised power 2. We have all the values, I guess, yeah? H positive concentration is given to me. How much is that? 10 power minus 3. So this is going to be 10 power minus 3 raised power 2. So 10 power minus 6 multiplied by. Fe dipositive concentration is also given to me. That's also 10 power minus 2. That's also 10 power minus 2. 10 power minus 2 raised power 2. It's going to be 10 power minus 4 divided by. Partial pressure of H2 gas. Partial pressure of H2 gas is 0.1. That means 10 to the power minus 1. multiplied by Fe positive concentration, which is 0.1, means 10 to the power minus 1 raised power 2. That means 10 to the power minus 2. Very, very simple. So it's going to be 10 power minus 10 in the numerator. In the denominator, it's going to be 10 power minus 3. So it's going to be 10 power minus 7. So 10 power minus 7 is the value of QC which I got. 10 power minus 7 is the value of QC which I got. Very simple. Now people, after getting the QC value, can we calculate E naught cell also? Can we calculate E naught cell also? Which is going to be equal to E naught of cathode minus E naught of anode. Right? Which one is my cathode? This iron, this electrode is my cathode. This electrode is my cathode. What is its standard reduction potential? Because we have to use the standard reduction potential of cathode and standard reduction potential of anode. What is the standard reduction potential of this electrode? Over here something is given to me. You have to check what is it. Is it standard oxidation potential or reduction potential? See guys, plus 2 to plus 3. Oxidation state is increasing. That means this is the standard oxidation potential. So I have to convert into standard reduction potential by multiplying it by minus. So it's going to be 0.17. Minus anode. Anode is my hydrogen electrode. And for hydrogen electrode, standard oxidation potential as well as standard reduction potential is taken to be 0. So I got the E naught cell value as well. I got all the values. I have to put these values into the net equation which I have. Let me erase this part. Let me erase this part. What is my net equation? That is E cell, EMF of the cell will be equal to E naught cell. E naught cell value I got as 0.17 minus 0.0591 divided by N value. N value we got to know as 2 log of QC. QC value how much I got? I got 10 to the power minus 7. Can't you solve it and get the answer? 0.17 minus 0.0591 divided by 2. This is going to be log of m to the power n, which is going to be minus 7. Log 10 is 1. This minus will come in the front. So it's going to be 0.17 plus 0.0591 multiplied by 7 divided by 2. Just solve this value. You'll get the value of EMF of the cell in volts. Let me know in the chat box if it is clear to you. Let me know in the chat box if it's clear to you. Yes, AVN. Yes, definitely. Yes, yes, yes. Absolutely. The channel is created for that purpose only. Thank you, Malik Fazan. Okay, VSG is getting 0.03769 volts. That's wonderful. Bhanu Prakash is getting 0.08. Bhanu Prakash and VSG, always you guys are getting the different answers. I don't know why. Right now, Surendra got also a different answer. I don't know why. Puppy is getting 21.17. Okay, whatever the answer comes, you can keep that, okay? This is something which you have to solve. 0.17 plus 0.0591 multiplied by 7 divided by 2. This is something which you have to solve. Got it? Okay. Should I move ahead? Should I move on to the next question, guys? Puppy, I'm just solving the question, bro. I'm not looking at anyone's comments. All right, guys. Let's solve one more question then. Let's solve one more question. Okay, this is the question which is on your screen. Not this one. This is going to be your next question, which is going to be your homework. I have to solve this one, right? Okay. See, guys. The EMF of the cell is 0.81 volts. The EMF of the cell is 0.81 volts. The cell which is given to me, metal solid changed to Mn positive aqueous, whose concentration is 0.02. On the right hand side of the salt bridge, we have got H positive aqueous whose concentration is 1 molar. It is changing to H2 gas, which is at the pressure of 1 bar. Calculate the charge on the metal. Calculate the charge on the metal. We have to calculate the value of N. We have to calculate the value of N right here. Okay? And we are given with few values. E naught of M changed to Mn positive. That means you are given with the standard oxidation potential of this electrode as 0.76, right? So first thing which I'm going to do, I'm going to convert this SOP of the electrode as into standard reduction potential. This is going to be E naught of Mn positive changed to M will be equal, it's going to be minus 0.76 volts. Minus 0.76 volts. This is first thing which I did over here, right? Now, see guys, the same procedure The same procedure which we followed in the last question, okay, same procedure I'm going to follow here also. See, first thing, on the left hand side of the solid bridge, I have anode, okay, and at anode, what takes place? Oxidation takes place. At anode, I would say oxidation is going to take place. Metal is changing to Mn positive. If metal solid, if it changes to Mn positive, then it has to lose electrons, right? It has to lose electrons because this is the reaction which is taking place in anode, oxidation reaction. So it has to lose how many electrons? N electrons it has to lose. Very simple. Okay. What about the cathode, guys? What about the reaction which is going to take place at cathode? At cathode, reduction will be taking place. At cathode, reduction will be taking place. And cathode is your hydrogen electrode. And in the last session, I've told you when hydrogen electrode acts as a cathode, what reaction takes place there? Reaction is going to be twice H positive aqueous plus 2 electrons change to H2 gas. This is the reaction which is going to take place at cathode. Very, very simple. Yeah, exactly. This is the reaction which is going to take place at cathode. Now people understand. Can I directly add the two reactions? I cannot add the reactions unless electrons are balanced on both the sides. Over here we have got n electrons. Over here we have got 2 electrons. So I am multiplying the first reaction by 2 and second reaction I am multiplying by n. Correct? After multiplying the reactions, I'm going to add them. So net cell reaction which I'm getting over here, that's going to be twice metal solid plus this is going to be 2n times H positive aqueous. 2n times H positive aqueous. This is going to be 2 times Mn positive aqueous. 2 times Mn positive aqueous plus n times H2 gas. Plus n times H2 gas. This is my net cell reaction over here. Okay. Now people, if I'll ask you how many electrons got cancelled over here? How many electrons got cancelled over here? Very simple. This will become 2n. This is going to become 2n. This is going to become 2n. 2n got cancelled. So how many moles of electrons are being exchanged over here? 2n moles of electrons are being exchanged over here. 2n moles of electrons are being exchanged over here. Right? Now guys, understand. This is the net cell reaction. Can I write QC value for it? Can I write QC expression, reaction quotient expression? Mn positive, right? Which is an aqueous form. I'm going to use its concentration. Concentration of Mn positive raised power 2. This is H2 gas. I'm going to use its partial pressure. So partial pressure of H2 gas raised power n, stoichiometric coefficient is n, divided by. This is metal solid, done, nothing to do with it. This is H positive. I'm going to use concentration of H positive to the power what? To the power 2n. Very simple. Okay. What about the concentration of Mn positive? Concentration of Mn positive is given to me as 0.02, or I can write it as 2 into 10 power minus 2. Square of it. Multiplied by partial pressure of H2 gas. Pressure of H2 gas is given to me 1 bar, nothing to do with it. H positive concentration, how much is it? That's also 1 molar, nothing to do with it. So I got the value of reaction quotient at 4 into 10 to the power minus 4. This is what I got the value of reaction quotient. Very simple. Okay. Now, I'm going to calculate E naught cell now. I'm going to calculate E naught cell, standard EMF of this cell, which is going to be equal to E naught of cathode minus E naught of anode. Right? And for cathode and anode, we have to use their SRP values, standard reduction potential values. Cathode is my hydrogen electrode. What is the standard reduction potential of hydrogen electrode? 0 minus. Anode is my metal electrode right here. Its standard reduction potential is this one, which is minus 0.76. So it is minus 0.76. Can I say the value over here will come as 0.76 volts? This 0.76 volts is the value of E naught cell. It is the value of E naught cell, right? I got the value of E naught cell, I got the value of QC, I have the value of how many electrons are being exchanged. I can use all these values in the Nernst equation, right? See guys, when I'll be using all these values in the Nernst equation, what am I going to get? I'm erasing all this, okay? As per Nernst equation, E cell is equal to, E cell is the EMF of the cell, and the EMF of the cell is given to me, that is 0.81. E cell is equal to E naught cell. E naught cell I got as 0.76. Minus 0.0591 divided by, should I write n or 2n? Divided by n or 2n? Divided by 2n, because 2n electrons are being exchanged from anode to cathode, right? So it's going to be 2n. 0.05 n1 divided by 2n. This is going to be log of QC. QC value already you have, that is 4 into 10 to the power minus 4. Correct? You have all the values, I guess. Okay, all the values we have, we just have to calculate the value of n. We just have to calculate the value of n. We just have to calculate the value of n. So it's going to be equal to how much? It is going to be equal to, let me show it to you. This will be 0.81 minus 0.76, 0.81 minus 0.76 multiplied by 2n, divided by 0.0591 will be equal minus times log of m into n, which is going to be log of m plus log of n. This is something which I got. Right here. Correct? Very, very simple. Over here, you will get the value as 0.05. 0.05 multiplied by 2, that is 0.1. So it is 0.1 multiplied by n. 0.1 multiplied by n divided by 0.0591 is equal to minus times log of 2 square. It is going to be 2 log 2. 2 multiplied by log 2. Log 2 is 0.3. 0.3 multiplied by 2 is 0.6. Correct? 0.6. Okay, this is going to be minus 4. This is going to be minus 4. So on the right hand side, the value over here is coming as, it will be coming as minus 3.4 minus plus, so 3.4. Over here you are getting the value as 3.4. Correct? So you just have to solve this equation. You'll get the value of n right here. N value you'll be getting 3.4 multiplied by 0.0591 divided by 0.1. Okay, this value approximately you are going to get as 2. Okay, and this n we were supposed to calculate, which is the charge present on the metal atom. Is it clear, guys? Is it clear? Let me know in the chat box fast. Let me know in the chat box if it is clear to you or not. Hi Paras, how are you? Banu Prakash, n value will come as 2. Yeah, exactly. Yes, absolutely. N value we got as 2. That's what we were supposed to calculate, right? What is n basically? What is n? N is a charge present on the metal. This charge we were supposed to calculate. So we got the n value as 2, correct? Yes, great. Okay, so people, the time is up. I've already taken 15 minutes extra of yours, but I'm giving you one more homework. This is your homework, guys, and do let me know its answer in the comment section afterwards. Okay, so 2 questions are there which are going to be your homework, right? The same concept you are going to use. You are given the complete cell. Calculate the mass of NaOH required to be added. Calculate the mass of NaOH which must be added to the cathode to consume all the H positive ions in the following cell. Cell is given to you. Just calculate the H positive concentration from here by using the Nernst equation. Okay, H positive concentration, if you will calculate, you will get the number of moles of H positive. Then equate number of moles of H positive with the number of moles of OH negative. Get the mass of OH negative. Get the mass of NaOH. Right? I just gave you the hint, idea I gave you. Rest you can do. And let me know the answer in the comment box afterwards. Got it? So 2 questions you have to solve, guys. And do let me know the answers in the comment box afterwards. Okay? So I think the time is up. It's high time to take the leave now. Banu Prakash, tomorrow's class topic. Tomorrow we are going to talk about concentration cells. That's again important. Okay? Concentration cells. Tomorrow we'll talk about. Okay? I'm sure all the doubts, everything is clear to you. I'm sure about that. Yeah. So I'll see you guys tomorrow again at 5:30. And in tomorrow's class, we'll be finishing one more important topic. That's what we call as concentration cells. Okay. All right, Matthew, I'll do that. First, you try these 2 questions. Let me know on my Telegram or Instagram, wherever you find me. Okay. I'll be sending you the solutions of these 2 questions if you cannot do them. Okay. Chalo, take care, bye-bye, see you. I'll see you guys tomorrow at 5:30. Till then, bye-bye, take care, God bless you all and love you all. Take care, guys, bye.